Everybody say hi.
Are they on Zoom?
No. Oh, no. No, this is not Zoom.
No.
We ain't doing synchronous crap. This is just video.
Oh, okay.
So you are recording Monday, Wednesday, Friday, and posting those? That's the plan?
I didn't record on Monday because I didn't do nothing except this. And right now, this is a stupid video. I mean, you're going to be like fast forwarding through this crap. So I'm not sure how well this is going to work. Because one of the things I so miss is this momentary, well, it's been now 35 minutes, but this momentary interaction with people where I can say, okay, we're not going to be doing lab. Or, hey, this is how I would work this homework problem. Or, Quinkle. Because now I have lots of people asking me about it, and I can explain it one time. I may devote a whole video to it. And so that's something that's really useful. Lecturing, is an important thing. Whether that's going to work this way, I don't know. I should be able to edit this, but I can't. But, what the heck? Now I have these gigantic markers. But I'm not sure you can hear me if I'm stepping back this far, because in 326, I have my VCR right in front of me, and I don't have as much whiteboard, but I know everybody can hear me. This may be a test video. Oh, now, is this an iPad or is this one of those dedicated?
No, this is an iPad.
Okay.
But then I bought a note app for it. So
Cool. Because I think the typing doesn't work. In terms of like putting it in your head. Let's do a little bit of sciencing and see what happens. And then there's these things. And look, we know that the virus is not captured by a HEPA filter. Now, you can't capture viruses by filter. Sorry. Now, if it had a UV light, it might work. But the dwell time isn't long enough. It's theater. Sorry. Yes?
Is there, like, from our book, like assigned readings or anything that you'll, like, tell us that will complement your lectures and things? Or are we supposed to just kind of, like, find it in the book? Or
I was going to say something like a real snarky smartass, but I do list, I think, the book chapters on here. And I don't know what kind of book you got. Virtually any version of the book, short of like the first and second edition, they actually did a fairly big rearrangement, will work. So I've got a variety of editions. But yeah, we're looking at chapter 2.
okay.
And frankly, I cover chapter 4 a lot in my discussion of chapter 2. I don't know why they did that, but yeah. So yeah, I think that the book is a good ancillary resource. Another thing that I have sort of outline notes for each chapter, but I usually give those like the week or so before the exam, because I don't want you to have that as like your only source. Again, it's all about you writing things down. So, yes.
Sorry. So the current plan is like Monday, Wednesday, Friday would be separate material, so that you would potentially record them and we would all.
I think so. Is that you'll be live for one lecture, and then you will watch the other two.
And then did you say you were going to record other ones too without?
I don't know. I mean, in a normal semester, I actually end up being like a week shy, and I do in lab, like our cytoskeleton lecture stuff. I'm not sure how it would go down, and I am not sure how effective this is going to be, because looking at this now, like, this is pretty stupid. But the other side of this is, when I'm done here, I'm going to go upstairs and re-lecture. And so, because otherwise, what are we going to do? I mean, you're going to ask me questions. So, does the tRNA bind here, or does it bind? I don't know. I mean, you might, I guess. Let's see how it goes. Because it may be there's an advantage to being in class, or maybe a disadvantage. You got one of 3 that is either good or bad, or they're probably about the same. I'm not sure how well this is going to work, but I'm going to give it a shot, at least for now. Let's start with the basic atomic structure. So you've had basic chemistry, and I said, I bet you're not going to be able to hear me or see me. This is great. So I bet I'm going to be doing recorded lectures,
Okay.
and then sort of doing it over in here, maybe. I haven't decided yet. Because I like actually having this, but it's a bit rambly, and to have to watch it would probably be really bad, and I'm not sure you can see anything from there. So, okay, atomic structure. You had basic chemistry, but this actually gets to some of the important terms we're going to be using. And first off, the structure of the atom, the atomic nucleus. We've got the proton, which is, of course, positively charged, and we have the neutron, which is no charge. Fairly basic stuff. Then we have the electron, significantly smaller, carrying a negative charge. Now, one thing I read a while ago that I think is kind of a cool analogy, and you may or may not have ever seen this and everything, in terms of size, if we think about the atomic nucleus, we can imagine that we're on a football field. So we've got 100 yards. We're standing right there in the middle of the 50-yard line. And this is a domed stadium. So you got the big dome above you, and because we're imagining this, the dome continues, and it's actually a sphere. So we're standing in the middle of a sphere, 100 yards in any direction. You know, the skybox is way up there, a whole bunch of space. And this is what standing in the middle of an atomic nucleus would look like, a lot of room. And so we can take a basketball, sort of relative size here, and put a big red plus on it, bounce that on the 50-yard line, put it down, then take a pretty much the same size basketball, put an N on that, that's a neutron, put that down, and then take something between the size of a ping pong ball and tennis ball, and put a negative sign on that, and throw that into the ceiling. And it begins zooming around. Now, it used to be thought that it was zooming around because of the same kind of orbital mechanics that planets move around the sun. No, it is weak forces, and the electron is moving about. And really, there is no dome. The dome is, in fact, being visualized by the path of the electron. So the electron is moving around, creating this dome. That is how much space there is in an atomic nucleus. I mean, a lot. Now, if we have one proton and we have one neutron, and we've got, zooming around this, one electron, we have created hydrogen. Okay, here's a freshman chemistry class question I'll ask you. How do you define an isotope? Anyone? Bueller? Ooh. I like that as my definition as well. That if the number of protons doesn't equal the number of neutrons, you have an isotope. Because there's a couple of things that fall out from here. Is that the proton number, that is what determines an element's identity, right? And I mean, that's why we have the periodic table. So elements change identity based on the proton number. But you can add or subtract neutrons and not affect the element's identity, the way it's going to behave chemically. And so my definition, although I'm not sure it's always the definition, of an isotope is somebody in which the neutrons don't equal the number of protons. Now, I think a more nuanced definition of an isotope is the most common form of it in the Earth's crust, or on the planet, is considered the element, and then anybody else is not. And the reason I say that is because I used to draw this as hydrogen, and it turns out that the most common form of hydrogen on the planet is just that, a proton. And when we're talking about hydrogen in solution, that's really all we're talking about. So when you see the symbol H+, that really is, in fact, just a naked proton. We'll be talking about the proton pumping mechanism. And with acids and bases, you have protons changing. It really is just a proton. That's all there is there. So this is the hydrogen atom, and the most common form of it is, in fact, this. Now, if we add a neutron, and this is where I go, I don't like this, but I think this is the truth. This actually becomes the isotope known as deuterium. And if we put a third in, or a third subatomic particle, a second neutron, this is known as tritium. So, for several years before I looked at the book and went, I was drawing deuterium as having 2 neutrons and tritium as having 3. I said, hey, it ain't that way though. And it's because science, chemistry. The chemists are always mucking things up, All right, so we have isotopes. And sometimes they're stable, sometimes they're not stable. They can kick out a neutron, they can kick out a neutron and a proton or 2 protons, a whole range of things that can happen during radioactive decay. And we'll be talking a little bit about radioactive tracer experiments and things, but not too much. Anyway, there you go. So the main point was the proton number. Now, let's think about this from our football stadium basketball perspective. We've got I have another 2 minutes. We got a lot of room here. And so you put a second basketball on there with a plus sign. You're now standing in the atomic nucleus of helium. You add a third, and are you boron? Regardless, you keep on adding these basketballs, and you keep changing elemental identities. Now, at the moment, there are, I think, 110 elements that have been discovered, and only 70-something are naturally occurring. The rest of them are built by smashing different atoms together and blasting more basketballs onto the 50-yard line. And if you think about it, there's a lot of space there, and so we could build, theoretically, really big elements. And there's various discussions that there's some elemental stability islands out around 120 or so, because these guys that are like 110 and down to 90 are real transient. They're there just for moments and they disappear. So that's elements. And one of the things I think about when I begin starting at this very base level, which I really don't have much of a sense for, is there really is nothing there down there. And theoretically, I should be able to just pass my hand through stuff or walk through walls because there's a ton of space here. It seems like I can't yet, but I'll let you know if I figure out how to do that. So the next point then, and we'll pick this up when we next meet, is going to be getting into how we can make bonds and the structure of the atomic bond. And that has a critical role as we start talking about macromolecules. But we will stop here. So that was 14 minutes exactly, and of that, probably about